Okay, here we go. So today we are going to solve factored equations. So this is really just a review. It's going to be a nice refresher course on something that we learned before. And we'll talk about why this is super important, why this is super helpful. And will lead to new material next week when it comes to how do we get these factored forms. Again, this is a lot of stuff is from Algebra 2. And we're going to just kick it up a notch for our pre-calc reasons. Here we go. So if I give you a problem that says 3x plus 2 is equal to 0, right? 3x plus 2 is a nice simple line. And we worked a lot in Algebra 1 of how can I solve for x to get x alone. And in this case, since it's equal to 0, we're going to just minus some values over, get rid of what's farthest away. 3x is equal to a nice -2. Then divide 3 to both sides. X is -2/3. Nice. Now, you guys might have enough experience to do this in your head. Absolutely fabulous. But I just want to remind you that being able to show all the steps is super important, especially, if we haven't done this in a while, right? It might be a little rusty. So I'm saying that x is -2/3, and if I plug in -2/3, the answer would become 0. Let's test it. 3 times -2/3 plus 2, would that lead us to an answer of 0? Well, nicely for us, the 3's divide out, gone, and we're left with -2 plus 2, and that is 0. That's a win for us. Now, what does this represent? If we went ahead and looked at a graph of the graph y is equal to 3x plus 2, which is our line in slope-intercept form. Let's go ahead and graph this out quickly. The graph would look something like 1, 2, put a dot, and positive 1, 2, 3 over 1. We see a line here. So what does this statement here mean? 3x plus 2 is equal to 0. Well, 3x plus 2 is equal to 0. That means y was going to be 0. And when y is 0, that's what we call the x-intercept. Or when will this line hit y is equal to 0? When will this line bury itself into the ground? And if you can look at this, the estimate looks like it's going to be kind of ish. When I fudged it a little bit, this is going to be -2/3. And we term this in Algebra 2 also as what we call a root. And when the graph hits the ground, we call those roots, almost like the roots of a tree or roots of a plant. And that's the point where the y is equal to 0 and the graph touches the y-axis. Now, there are a couple cool things about this, is that 0 is super easy to solve for, right? Look, we just made equal to 0 and we used some skills from Algebra 1. Now, let's kick this up a notch and see if this is helpful to us graphing something a little harder. And let's go ahead and graph a parabola. If I say x or y is equal to x squared minus x minus, let's say 6 here, we have a skill of factoring. So let's go ahead and factor this problem. Two numbers that multiply to become 6 are 1, 6, 2, and 3. Which of these subtract out to become a 1? I'm seeing that 2 and 3 are the numbers I want to use. X, 2 and 3. And we need negatives to win, so I'm putting negative and a positive. Again, we'll go over factoring again. This is something that we learned in Algebra 1 and Algebra 2. I try to teach my kids, you guys as my kids, how to factor quickly in your head. So I always look at the last number first. Two numbers that multiply to become 6 is 2 times 3 and 1 times 6. Do any of these possibilities subtract out to be 1? Yes, 2 and 3 subtract out to be 1, so I know I'm for sure going to use 2 and 3. Now, next part is making sure I get the correct sign. I need more negatives than positives. To double check it, if I multiply x times x, that's x squared. X times 3 is -3x. 2 times x is 2x, and 2 times -3 is -6. And if you take a look here, we have more negatives, don't we? So you want to make sure you pick the correct sign for the correct number, so we end up with more negatives or more positives depending on our result. X minus x minus 6, which is what we had, okay, just to double check. Okay, now that we have y is equal to x squared, x plus 2, and x minus 3. Now, why is this so important to us? Well, one thing is, can you guys imagine what the graph of this parabola will look like? Sure, it's some type of U-graph, but where on the graph would this be, right? Where would this be? What part of the graph would I graph this at? And there's no real values to start off with. Sure, you can say, I see negative 6, 1, 2, 3, 4, 5, 6, sure. But is the parabola this way, this way, this way? Like, the idea is that we need more information. And I could use completing the square, but factoring was one of our fastest ways in Algebra 2 in deciphering how to graph it. And what we say is, making the y value equal to 0. What if this graph was equal to 0? What numbers could we use to make these factors go to 0? Now, with your mental math skills, I know it's going to be really hard to pull it out of our winter break. But can you think of a number, blank plus 2 is equal to 0? Blank plus 2, I want you to go to 0, and x minus 3, I want you also to go to 0. And this was a trick that we had. And this trick involves something called the zero product property. And we'll talk about that in just a minute, now that after we see how easy this is. Our answers will be x is negative 2, and x is positive 3. Now, just to verify this, my claim is that this x minus 2 is going to make the function become a 0. Go to 0. That's my claim. Now, in the factor form, it looks obviously true. X plus 2, if I plug in negative 2, that's going to be 0. And 0 times anything else is going to be 0. But let's see, is this true in the original equation? If I plug it back in from here, is negative 2 squared minus negative 2 minus 6, would this become 0? Doesn't look like it. Let's go ahead and try it. Negative 2 squared is 4 plus 2 minus 6. 6 minus 6 is 0. Oh my gosh. Negative 2 was an answer. Let's try 3. 3 doesn't look like it. 3 squared minus 3 minus 6. Would this also become 0? 9 minus 3 minus 6. 9 minus 9. Oh my goodness. This is also 0. We can't just look at a problem anymore when it comes to x squared or x cubed or x to the fourth and automatically say, I know what the 0 is. Sure, for lines, this was pretty easy. 3x plus 2, I can say, oh, that's negative 2 over 3. Pretty easy. X plus 2, hey, x is negative 2. Pretty easy, right? Negative 2. I can do that in my brain. But when it comes to quadratics, anything bigger than x, like x squared, x cubed, it becomes a lot harder to do. So what we have a trick here is to factor it first, and looking at these factored forms, we can obviously tell a lot easier what our zeros would be for the problem. Example again, our negative 2 would satisfy our first factor, and our positive 3 would satisfy our second factor. Now, just to answer another question, sure, if I plug in negative 2, let's go to the factored version here. If I say, if I say negative 2 plus 2 and negative 2 minus 3, right? If I'm plugging in x as negative 2, well, sure, this is 0, but isn't this negative 5 here? Sure, I made one side 0. What about the other side? Now, here is the caveat here. Aren't these factors multiplying each other? Aren't they multiplying each other? So when I'm multiplying, what's 0 times anything? 0 times anything will always become 0. So one cool thing about this, us solving for 0, not for any other number, not for 5, 6, 7, 8, for 0 is that any number times 0, 0 times I don't care what this other guy is going to be, will always be 0. That's how we're able to separate the problem into two easier problems than trying to deal with them both at the same time. We never solve this problem for any other number than 0. If it's not 0, we rewrite it so that it is 0. If I give you a problem that looked like this, x squared minus x minus, let's do minus 5 is equal to 1. Okay. Even if I tried multiplying, being able to factor this, which I can't factor this, okay? How hard is it to pick a number times a number to become 1. To become any number, a number times a number to become another number. Imagine if I asked you, find two numbers and multiply to become 47. You have to start thinking about these crazy numbers. But what happens is for us, when we use it's called the zero product property. If I instead rewrite this to become x squared minus x minus 6 equals 0, whatever 0 times whatever number we get is going to be 0. And the zero product property says a 0 times any number is 0. So if I can make the first term go to 0, the first factor go to 0, or the second factor equal 0, we are going to make this problem a lot easier. Now, is every problem factorable? No. So we're only dealing with factorable problems in this first case. In the first 2 weeks, 3 weeks, we're only dealing with polynomials that we know will be factorable. So let's do this again. I'm going to give you guys a problem. Here we go. It's going to look like x cubed plus x squared minus, let's do something kind of cheesy, minus 20 is equal to 20x equals to 0. Okay. Now this is an x cubed problem. So we're going to factor what we can. If you see what's in common, we see an x and x and x. These will all have x's. So I'm going to take out the x first. And we're left with the problem x squared plus x minus 20. All right. Great. Let's keep factoring it. I could factor this. Two numbers that multiply to become 20. That subtract out to become 1. 20 and 1. 10 and 2. 5 and 4. Hey, 5 and 4 subtract out to become 1. So we know our terms are going to be for sure x, 5 and 4. We need positives to win. So I need more positives. So that's going to be a positive 5 and a negative 4 because we need a positive and a negative. Going to 0. Now the cool thing here is that I can solve for 0 pretty easily. That's going to be a negative 5. Over here it's going to be a positive 4. And here's a freebie. Whenever you have an x by itself, isn't 0 times anything? If this was 0, what's 0 times anything? It would still be 0. Okay, so this is from Algebra 2. So my terms, my values that would make this go to 0 are 0, negative 5, and 4. Now why is this helpful to me? Then this is just a preview about what we're going to do with these factored forms. Is that if I was trying to graph this, I know for sure that the y value is 0 when x is 0, when x is negative 5, and x is 4. Oops, went the wrong way. Don't we have 3 zeros in this graph? Okay, we have these 3 zeros. And with a little bit of work, we can see that the graph is going to look something like this. That's all the work we need to get a rough idea what the graph is. Sure, I don't know how high this goes, but that's not the goal of this. I don't know how low this goes. It could be lower, it could be even super lower. But I know for sure we have to cross through these 3 check marks at negative 5, 0, and 4. And that gives me a rough idea what this graph should look like. And that's our main goal in the next 2 weeks. Figure out what higher polynomial graphs look like using this root way of solving for it, looking for the roots. Okay, and this is really what your IXL is going to be. You guys are just going to practice solving for these factored forms. Let's do one more. X minus 6, 2x plus 5, and x plus 2. Okay, what would be the 3 x's that would make this function go to 0, or this equation go to 0? So we can write it out separately. Now, why can we set them all individually to 0? Because if this guy was 0, I don't care what these other guys are. 0 times anything is 0. If this guy was 0, I don't care what the other terms are. So we can set them each individually to 0 and solve for them separately. Here we go. The first term, well, x here would make this go 0. You could just do your simple algebra. Or you can just say 6. If you jump from here to here, 100% okay. Minus 5, then divide by 2. X is negative 5 over 2. If you jump from here to here, 100% okay. And x is equal to negative 2. So these are our 3 values that will make this go to 0. On IXL, you're going to go ahead and write this as 6, negative 5 over 2, and negative 2. Order does not matter, but you need to write all 3 answers, and you separate them by a comma. Okay. And that's it.